Hello. Let us see HHL algorithm, guys. HHL algorithm usually is used to solve system of equations. Okay. Use it to solve system of equations. All of us are aware of how to solve system of equations, guys. Usually AX is equal to B would be the system. All of us are aware of matrix theory. AX is equal to B would be the system. There are different ways, Gaussian elimination, um, a Cramer's rule kind of thing to solve the system. One version is this, that is X is equal to A inverse B. Okay, if A is non-singular. Okay, if I can find the inverse of A, then I can as well find X or solve system of equations. Of course, I'm talking about the classical method. The classical method of solving a system of equations. Okay. Uh, of course, in the classical method also, there's one more method. What that is uh, I'll talk about that and then come to HHL, guys. What that is classical method also. There's this way of finding uh, diagonalizing A. You are all aware of finding eigenvalues for A, right? That A minus lambda I'll be using, and then AX is equal to lambda X I'll be finding out. Once I get the eigenvectors, I form the model matrix denoted by P, guys, with the eigenvectors x1, x2, x3. Okay. Once I form the model matrix, what happens is uh, P transpose AP is what I'll find out. Of course, actually it should be P inverse AP, guys. But here, once I find eigenvalues and check for orthonormality or orthogonality of eigenvalues, I'm sorry, eigenvectors, P turns out to be orthogonal. Of course, you can have a question that, what, ma'am, if P is not orthogonal? I'll orthogonalize it by normalizing. How do I do it? I divide every eigenvector by its norm. Okay. And once I do this, P becomes an orthogonal matrix. Why? Because all these vectors all the vectors x1, x2, x3 have been orthonormalized or normalized, whatever. Okay. So once, what I'm trying to say, once P becomes orthogonal, P inverse and P transpose both are same, guys. Okay. Hence, what I will do is I will just form the matrix P, pre-multiply and post-multiply A with this P, and hence this reduces to a diagonal matrix, guys. See the property of the diagonal matrix. The diagonal matrix, diagonal entries are the eigenvalues. Suppose if I have three eigenvectors x1, x2, x3 corresponding to lambda 1, lambda 2, lambda 3. After I diagonalize A, I get the matrix, diagonal matrix whose entries are the eigenvalues. Okay. By the way, coming to classical method, what do I do is first thing is I'll be diagonalizing A. This is the process of diagonalizing A, guys. Second thing is, of course, in the process of diagonalizing, I'll be finding out lambda i's. Okay. Here, since I have A inverse, I also would be needing a lambda inverse. Reciprocate the eigenvalues. That's it. Okay. Once I reciprocate the eigenvalues, just compute A inverse B, which gives me the value of capital S. Okay, that's how I will do. Yeah, this is all about the classical method. Why I made about the classical method is quantum is also similar. I mean, HHL in quantum, by HHL, process is similar, but only thing is we do it in quantum states. Okay, I will write for quantum the method, how to solve the system of equations. I will just write. What is it that I do is, in quantum, what do I do is, first decompose, decompose, whatever, into eigenbases. You know bases, right? Computational bases, ket 0, ket 1, right? Decompose A, of course, I should say here A, decompose A into eigenbases. Okay. Once I decomposed it to eigenbases, I start finding out eigenvalues. Again, guys, here also I'll reciprocate the eigenvalues, but since it is quantum, I can't do things directly. Again, in quantum, things are in terms of electrons, atoms, or wave kind of things. Hence, I cannot directly reciprocate. There is a process, there's a system, or there is a procedure in which you reciprocate. Of course, it's all about taking the reciprocal only, taking reciprocals of the eigenvalues only, but in a quantum sense. Reciprocals of eigenvalues in quantum sense, I will write so that you are clear. Quantum sense. And then the final version is recombine or whatever. I have decomposed, done things. Again, I'll recombine and hence find the x. Or again, there's something called entanglement. I remove the entanglement. I uncompute and do things. Okay, that I'll come recombine to get the required value. That's the basic skeleton of HHL, guys. Okay, now let me stick on to the proper way of explaining HHL, not the random way or just the broader version. Okay, what do I do in the first step? First thing, we prepare the quantum states. Right, with the different colors so that, yeah. First thing that I will do in HHL, step 1, working rule, of course. What do I do? Prepare quantum state. Quantum state. Okay. Proportional to ket xi. Ket x. Okay. Ket x is some random state, guys. Okay. So, ket x. See here. What actually it was? Ax is equal to b. What I will do it? X is equal to A inverse B kind in my classical. Okay. Now here this X, whatever I'm talking about, that how will it be? Is A inverse ket B by norm of A inverse ket B. Okay. Normalizing, orthogonalizing kind of things. This is the quantum way again. Quantum way of preparing the state. Okay. Yeah. Now, of course, this is how I should get. Now, what I should do first? See, first I will reduce B to eigenbasis. Okay. Ket B is rewritten in eigenbasis. Rewritten in eigenbasis. How do I rewrite it? Please see here. Ket B is equal to summation I beta I ket ui. Okay. What are these ket ui's? These ket ui's are the eigenvectors. Eigenvectors of A corresponding to lambda i's. Okay. What I have done? B I have rewritten in terms of eigenbases. What are the eigenbases? They are nothing but the eigenvectors. Usually vectors form bases and all that, right? You know linear algebra. What is basis kind of things. Of course, here also we have computational basis about which I am talking, where the whole of quantum system depends on the qubits ket 0 and ket 1. Also the superposition state alpha ket 0 plus alpha ket 1. Okay, that's the step 1, guys. Anyways, let me stick on to HHL only because there are a lot of confusions for many of you. Yeah. Step 2, once I have reduced B to quantum basis, Next, what I will do is, I will apply quantum phase estimation. Okay. Quantum phase estimation. Again, your Fourier transforms, quantum phase phase estimation matrix, all those come into picture. Okay. Why I have done it, I will just tell you. Wait. Okay, we apply phase estimation on e power at, e power iat, unitary. This is a unitary thing, unitary matrix. Okay, I'll apply phase estimation on this e power i8. Or in other words, no, actually I should say like this. I've applied phase estimation on A, guys. That's why it has become e power i8. Okay, now you see how things will, how I should write. See here, summation I, beta I, ket ui. This I am applying it on phase ket 0. Okay, something like this I am applying. Quantum phase estimation. After quantum phase estimation, what happens you see? Beta I, ket ui, lambda I phase is what I will get. Okay. Yeah. What I have done, I have applied quantum phase estimation. What exactly has happened? E power IAT. It has become e power IAT kind. Okay. Now, again you see here, I have got lambda I, guys. Once I have got lambda I, what I will do? I need to find out lambda I inverse. Okay, I need to find eigenvalue inversion. But then in quantum, it's not just reciprocating the number also, because the numbers can be complex and then things are different when it comes to a complex plane. Okay. To compute A inverse, we need to divide each eigenvalue, or we need to reciprocate each eigenvalue. Okay. First, this quantum phase estimation, what exactly it does is, it has extracted from the quantum basis. Quantum basis karna, I should say, from the eigen basis, it has extracted the eigenvalues. Okay. Yeah. It has extracted the eigenvalues. Quantum phase estimation has extracted the eigenvalues. Now, these eigenvalues are stored in a phase register. Okay, that's why I have written their phase. They are stored in a phase register. Leave about that. Let's come to the next step. So that again there is no confusion and again this doesn't become tedious. Yeah. In step 3, what do I do is, eigenvalue inversion has to be done now. Eigenvalue inversion has to be done now, for which what we will do is, we attach an ancilla bit and perform a controlled rotation depending on lambda I. Again, if you ask me, for just inverting an eigenvalue, why you are doing such a hectic thing? It is the quantum way of doing it. What I will do is, I will attach an ancilla bit. Chudandi ikkada, just look here. Lambda I to this eigenvalue, I will attach an ancilla bit. Or I will attach an ancilla bit, I mean the zero, get 0 bit, okay, to lambda I. And what I will do, I'll perform a controlled rotation. Okay, of course, there is a condition why the controlled rotation is like this. That also I will justify. What the condition is C by mod lambda I value should be less than or equal to 1. Okay, because of which I will perform controlled rotation. What happens is, lambda I, this becomes 1 minus C by lambda I whole squared associated with ket 0, guys, plus, this is a superposition state, C by lambda I ket 1. Okay. Yeah. Now if you see, Mod alpha squared plus mod beta squared should be 1, na? Okay. You can verify mod alpha squared is this, mod beta squared is this. Of course, depending on whether the value is turning out to be complex or real, you will verify. You will accordingly take what that is mod alpha squared plus mod beta squared value should be 1, right? When I'm going with the superposition state, you can observe that. You can observe that, guys. Okay. Yeah. Now, what is this? What I have done, first thing is I have formed the eigen basis. Again, eigen way of doing it. No, quantum way of doing it. I formed the eigen basis. How did I form the eigen basis is I have rewritten. Just see here what I have done. I have rewritten ket B as sum of eigenvectors kind, some alpha into eigenvector kind or linear combination of eigenvectors. I have written ket B as, which is called the eigenstates, guys, eigenstates, right? Now, after that, what I have done is on A, I have applied quantum phase estimation. Quantum phase estimation, if I have to apply, what I have, this eigenstates, whatever are there, eigenbases, whatever are there, beta I, ket ui, that I have applied on, I have assigned to ket 0 phase. Okay, assigned, what should I say? Yeah, what I did is I have assigned it to ket 0 phase. Of course, after quantum phase estimation, what's happening? This ket 0 phase, no, I think, ket 0 ancilla, whatever. Ket 0 ancilla, this should be, I think. This is giving me the eigenvalues, guys. See the difference from my LHS to RHS. Once I perform quantum phase estimation, I am landing up with eigenvalues. Once I have the eigenvalues, for A inverse, I will be needing lambda inverse. Of course, in quantum, things are related to atoms, electrons, or waves. At the same time, any number is not just a real number, it's a complex number satisfying all the criteria, basic criteria of quantum. So, I just cannot invert an eigenvalue just like that, write the reciprocal of it, for which I perform controlled rotation. Okay, controlled rotation I perform on lambda I. How I will do it? Ancilla bit. What do I do is, for the eigenvalue, I attach the ancilla bit and perform controlled rotation. Of course, ancilla stands for the temporary storage or whatever. Once I perform controlled rotation, what happens is I'll end up with the right hand side. What exactly is the right hand side? Is the superposition state, of course, satisfying the condition that C by lambda I is less than or equal to 1. Also, mod alpha squared plus mod beta squared is equal to 1. That condition also is satisfied because it is in superposition state. For superposition state, that condition is all the time valid, right? Once I performed controlled rotation, guys, what happens is this rotation generates 1 by lambda I. Okay. Where it will give me is into the ancilla amplitude, it will generate 1 by lambda I. Okay. Hence, what will I do? Once I'm done with that step, now I'll write the step 4, guys. Step 4, I have written something in the broader sense. Now here, what I will do is, I will uncompute. What is uncomputing is, see, I'm considering only this ket 0. Okay, because I'm attaching ket 0 ancilla, I'm using only ket 0. There are other things related to ket 1. Okay. What happens is, if you leave them as it is, what happens is they get entangled in between themselves, and the output that I'll be getting, I may not be able to predict. Once they start entangled, once they get entangled, one behaves like the other. Okay. So what happens is, I'm not interested in the remaining things other than ket 0. So what I do is I uncompute. I uncompute so that entanglement is removed. Further entanglement is removed. Further entanglement is removed. Okay. So what happens? Just see here. Get beta I, ui, get lambda I. Okay. Of course, I have got 1 by ket lambda I also in the ancilla register. Okay, after uncomputing, what happens? Uncompute. What happens is summation I, beta I, just see here, 1 by lambda I, ui, ket 0. Okay. Only this remains. Remaining things I will neglect. Uncompute and I will neglect. So what happens here once I have got this, I can clearly see my lambda has gone reciprocated to, what happened to my lambda? It got reciprocated. So what I'll be getting is beta I by lambda I ket ui. Okay, this is the measurement of ket 0, guys. Okay. What is the value or probability of ket 0, measurement of ket 0? If you ask me, this is it. Okay, once I get this, my job is done. Okay, this is what I wanted. Once I get the reciprocal of lambda, I am done with the answer, guys. This is my answer. This is my ket x answer. Okay, that's how I will do it. I hope it's clear. Okay. In case in case if there is some problem, I can just draw the circuit diagram and show. And I think with that I will just close because too much explanation again also complicates things. Okay. I will just show the circuit diagram. Yeah, just see here. See, these are the things that I have. Of course, A can be capital A also, guys. Okay. Now, what I'm doing is quantum phase estimation. I am doing. Okay. What will happen? Just see. Of course, B I have reduced to eigenbasis. That's what is that's what is the understanding, right? So what happens? Just see here. I'll be getting lambda J. Okay, ket 0 is as it is. Uj. Okay, eigenvalues and the eigenvectors. Of course, quantum phase estimation results in spectral decomposition kind, you can say. Now, next what I will do, I'll perform controlled rotation. Okay, controlled rotation gives me what? Summation j, beta j, lambda j tilde. Of course, this thing, controlled is nothing but remember that C appears. How do I remember, ma'am? That C appears. Controlled when I say C appears. Okay. Whole squared ket 0 plus C by lambda j ket 1. Okay. After controlled rotation, this. The superposition state I have got. I am not interested in the superposition state. I just need only ket 0. Okay. For which what I will do is I will uncompute. Uncompute to avoid further entanglement. Okay. So what I will get, just see, once I uncompute, ket 0 phase will have summation j beta j, okay, into C by lambda j ket 1 ancilla uj plus and so on, things will be there. These are all ancilla 0. Ancilla 0 is equal to 0. Whatever. Those things what we are doing, we are discarding, guys. I think I said the other way. We are considering ket 0. No, we are considering ket 1. Okay. And discarding ket 0. Ancilla is equal to 0. Whatever is there, that I am neglecting. Okay, when I am uncomputing in that stage, I am neglecting some things, considering only this. So finally what happens is, Now if I measure, I should say here measure. How do I measure? I take the coefficient, right? Measure ancilla 1. Measure ancilla 1. So what do I get? What are all there for ancilla 1? Summation j beta j c by lambda j get uj. Measurement means what? By its norm also I will take na. J beta j c by lambda j get uj. Okay? Okay, guys? Yeah. Now finally I understand that this answer is nothing but the answer for my ket x. Because see here, ket x is nothing but A inverse ket B, right? See here, ket x is nothing but A inverse ket B. If I have decomposed A into eigenvalues and all the things, it is nothing but lambda inverse ket B. Also, guys, you can see here, I will write like this. See, Ax is equal to Ax is equal to lambda x na. Okay. Now what do you do? Ax is equal to lambda x na. Now what you do is, suppose if I say A inverse x, guys, it is lambda inverse x na. Okay. So in the place of A inverse, I will be putting lambda inverse. X is nothing but my ket B, right? See here. That's how I have got. For A inverse, it is lambda inverse. Right? Why I am able to say clearly that it would be 1 by lambda inverses, because I'm starting with finding eigenvalues for A and hence the eigenvectors for A, and hence I am proceeding, of course, in a quantum way because of it. If you understand this, guys, HHL can be written in an extraordinary way. Okay, what is that? This circuit diagram, whatever is there, if you understand, you can write it in extraordinary, in your own way, you can express it, guys. Okay, that's why I've circuit diagram for HHL. Of course, this is there in the notes, but then understanding is difficult for you. I clearly understand. Okay. Yeah, I think this is it about HHL. You should understand. I stopped this video because it should not again go.